So here is another sample problem. So we have a mass spectrometer, so which can be used to measure the mass of an ion. So an ion of mass to be measured, and the charge Q is produced in source S, which is here. Oops. Okay, so the initially stationary ion is accelerated by the electric field. So yeah, here in this region, there is a voltage difference there. So there will be an electric field between the source S and this hole. In this case, the charged particle will be accelerated by the E field because there will be a Coulomb's force there. So the ion is accelerated there. So it's accelerated by the electric field due to the potential difference V. So the ion leaves S and enter a separate chamber in which a uniform magnetic field is perpendicular to the path of the ion. So this is the chamber, and inside the chamber we don't have electric field anymore, but instead we have a uniform B field which is perpendicular to the moving direction of the particle. So a Y detector lines at the bottom wall of the chamber. So this orange part is the detector. So it will detect where the particle will touch on the detector. Maybe it is here, maybe it is there, maybe it is there. But only between this range. So so here we know that the magnetic field B is 80 millitesla, and the voltage here is 1000 volts, and the charge is 1.6 something times 10 to minus 9 coulomb. Strike the detector at point that lie at 1.6 point something meter. So what is the mass of the individual ions in atom mass unit? So 1 U is actually 1 proton. Yeah, 1 proton. So here there will be we will have a conservation of mechanical energy, which is delta K plus delta U should be 0. So this is a conservation of mechanical energy. So this is originally this is at rest. So K initial should be 0, and at this point it should be 1/2 mv squared. So this is 1/2 mv squared minus 0, which is 1/2 mv squared. And delta U will be QV, should be minus QV, because at this point the electric potential is higher. So, and at this point the electric potential is the lowest place. So all the electric potential energy convert to the kinetic energy of the particle. So we have an expression like this. So we will have V equals square root of 2QV over M. And of course this is a circular motion, and we can use the equation as R equals mv over qb. And now we know that v is the square root of this term, so we have m over qb times the square root of 2qv over m. So in this case, we can cancel something. We have square root of 2mv, and then we have q, and then 1 over b, which means we can multiply m inside so that it becomes a square root of m squared, and then cancel with 1 of the m. And then also q becomes a square root of q squared, and then cancel 1 of the q, so that finally it looks like this. And actually we want to find m. We want to find m. And actually what we know is x, so x equals 2r, because x is the diameter and x is the radius. So actually x should be 2 over b square root of 2mv over q. So in this case, finally we will want to find small m. Small m would be x squared b squared multiplied by q over 8v. So x is 1.6254 times, b is 80 times 10 to the minus third power quantity square times 1.6022 times 10 to minus 9 over 8 times 1000. So this would be 3.3863 times 10 to minus 25 kilogram. And then we would like to express it as u. So we need to divide this number by 1.66 times 10 to minus 27th. So it would be 203.93 u. Any questions? So next we talk about the cyclotron and also the synchrotron, which is two types of particle accelerator. So actually, the synchrotron, we can see the synchrotron here. So we can see here is there is a source in the middle. To generate a particle to be accelerated. And then, so we have two D shape, one D shape here and the other D shape here. Within this area, we will generate the uniform B field, which is out of the page. So that in these two regions, the particle will have a circular motion. But there is a gap in between. Maybe I can slightly draw it here in a larger way. So we have a gap in between, and we have a D shape, which is two half circle. So at the very beginning, we have the source will generate a particle, and between this gap, there will be an alternating E field, which means sometimes it will point to the left, sometimes it will point to the right. It will be like at the beginning, the E field point to the left. The E field point to the left. So this particle will go to this way and accelerate. Go in this way and accelerate. So at this point, up to here, there will be no E field and only B field there. Only B field there. So there is only B field. Uniform B field there. So you can see the particle will have a circular motion. Will have circular motion. And up to this point, now the E field will change the direction to the right side. So from this point to that point, the particle will accelerate. Will accelerate. And then up to this point, there are only magnetic field, so it will be will have circular motion. However, at this point, the velocity becomes larger. The velocity becomes larger, which means the radius will also be larger. So in this case, it will have a larger radius. And then up to this point, the E field also point to the left side. So the particle will accelerate again. And then repeat this procedure so that the radius will become larger and larger. And then the radius will also be larger and larger. So this is the mechanism of the synchrotron, how to accelerate the particle. So that we need to control the E field inside this gap periodically, so that the particle can keep accelerating. Otherwise, if the control is not good enough, the timing is not good enough, maybe the particle go to this point, it need to accelerate to the right side, but still the E field point to the left side, then it will decelerate the particle. So it needs some sort of a control mechanism, or maybe you can just keep I'm not sure, maybe just keep the E field point to the left side at the bottom part and E field point to the right side at the top part. So everything will looks fine. So this is the mechanism for this synchrotron, and it also tells you that we need, actually it tells you that we cannot just put E field point to the left side at the bottom and right side at the top. Really need to control sometimes all the E field point to the left side, sometimes all the E field point to the right side, periodically. So this frequency is called FOSC, F oscillation, and we need to control this frequency, because the T will be 2 pi r over V. 2 pi r over V. 2 pi r over V. And we have V here. So V and V will cancel. So actually, the period for the circular motion, actually, it takes half of the period to go for half circle. So, so actually, no matter how large the radius is, it takes T over 2. It takes T over 2, going from this point to that point and going from this point to that point, going for half circle. No, it doesn't really depend on the radius or the velocity at that point. So as long as we can control the oscillation frequency of the E field correctly, then we can make sure that as long as the particle goes to this part, the E field point to the left side, and the particle goes to this part and the E field point to that side, and then the particle will keep accelerating. So this frequency is QB over 2 pi m. So it's just like the 1/t, because you can just put it 2 pi m, 2 pi r, 2 pi r over qb is 2 pi m over qb. And actually F oscillation is just 1 over t. FOSC is just 1 over t. So it is a qb over 2 pi m. So we need to control the oscillating frequency of the E field. However, the limitation for this cyclotron is that we need to provide large B field for the whole disk. And as you know, for the B field, we need the power. So for large area, we need to provide large B field is not easy. So in this case, the limitation for this synchrotron is that the particle energy can be up to 50 mega eV. Which is relatively small. Yeah, because I'm not sure how large this can be. Maybe in terms of a meter or kilometer. I'm not really sure. Yeah. So the next type of the particle accelerator is called a synchrotron. So for the synchrotron, not sure. There's no graph here. So actually, the synchrotron is like rather than a whole disk, we only have a ring. So we only generate the B field inside the ring. However, we need to control. We need to have better control to the B field and the oscillation frequency. Otherwise, the particle may collide with the wall of the ring. So, of course, if it is collide, then it will much decelerate. So the magnetic field and the oscillating frequency, instead of having fixed value as in the conventional cyclotron, are made to vary with time-varying accelerating cycle. So in this case, we only need to generate a B field in a smaller area or smaller volume, so that the B field there can be much stronger. However, we need a more complicated control so that this B field is time varying and avoid the particle collision with the ring. So the proton follow a circular, not a spiral path. So this is called a spiral 螺旋形的. So the radius become larger and larger for every loop. But here, it is a circular path. We only control the B field, so that to maintain the R to be constant, because as long as V become larger, then the B also need to become larger, because M and Q doesn't change. So as long as V is larger, we need to increase the B to make R to be a constant. Otherwise, it may collide with the ring. Yeah. So circular path, however, still must be large if high energy are to be achieved. So the beam is then injected into the PSB, proton synchrotron booster, which accelerate the proton to 1.4 giga eV, followed by the proton synchrotron. So we push the beam up to 25 gigaeV or gigaeV. So this is up to 50 mega eV. So this is 25 gigaeV, which is 500 times larger. 500 times larger. So this is the basic concept of the synchrotron. And maybe you ask why we need to accelerate the particles to a very, very high speed, because the physician really want to disassemble the particles. In chemistry class, you may know we have a proton, we have a neutron, we have a electron. But actually, the physician trying to find some more fundamental building block, like the quarks, and they really need to make some particles to collide with each other, so that they may break up to be some smaller building block. It's just like I ask you, if you want to disassemble your phone, maybe you can just pick up some tools, then you carefully try to disassemble it. Maybe you take 1 hour, 2 hours to disassemble your phone. But the quickest way to disassemble your phone is that you pick up your phone and then you crash it on the floor, and then you boom, and then you can disassemble it very quickly. This is a not so good analogy, but actually that's why they want to have a particle accelerator. So next we have another sample problem. So suppose a cyclotron is operate at an oscillator frequency of 12 megahertz and radius r to be 83 centimeter, or not so big, only half a meter. So what is the magnitude of the magnetic field need for deuteratron, which means one proton and one neutron, to be accelerated in the synchrotron? And cyclotron and deuteratron mass is roughly 2 times of a proton. So here, for part A, we have a B equals 2 pi m FOSC over Q. Because here we have the expression like this, so we just move all the terms to the left side except B, so that we can have B like this, and we can plug in all the values. So we have 2 pi times 3.34 times 10 to minus 27 times 12 times 10 to the 6th power, and then over one proton, one neutron, which means 1 E, which is 1.6 times 10 to minus 19. So B is 1.57 Tesla. So next, what is the resulting kinetic energy of the deuteratron? So actually, we can also find it like we have R equals mv over qb, so that we have V equals R qb over V over m. So we can plug in all the values. So we have 0.53 times 1.6 times 10 to minus 19 times the B is 1.57, and then M is 3.34 times 10 to minus 27. So this V is 3.99 times 10 to the 7th power meter per second, which is quite fast. If you can remember, the speed of light is 3 times 10 to the 8th meter per second. So it is more than 1/10 to the speed of light. And in that case, k equals 1/2 mv squared, which should be 1/2 times 3.34 times 10 to minus 27th, and then times 3.99 times 10 to the 7th power quantity squared. So it should be 2.7 times 10 to minus 12 joule. And if we divide this term by 1.6 times 10 to minus 19, so it is 17 mega eV. 17 mega eV. So it is not really large. It tells you that it can accelerate up to 50 mega eV. So for this case it is 17 mega eV. Although the speed is already quite fast. And actually, this kind of value is not very accurate. I need to say. And although this semester we will not cover the special relativity, 狭义相对论 special relativity. Actually, as long as the particle move close to the speed of light, then we need to consider the relativistic effect. If we still use the classical mechanics, then the value we got will be quite inaccurate as long as the speed of the particle is faster and faster. If the speed is quite low, then using the classical mechanic would be good enough. But for this kind of speed, more than 1/10 to the speed of light, this kind of calculation might not be accurate enough. So next, we talk about the magnetic force on a current carrying wire. So here, if we suppose we fix a wire here, and if there is no current, and even we apply some magnetic field, there won't be any force acting on this wire. However, if there is some wire going through the wire, if there is some current going through the wire, then there will be a force acting on the wire, because you can imagine the Coulomb force is like as long as we have current going from bottom to top, which means that there will be some charge, negative E, going from top to bottom, which means this is the velocity of the negative charge. And B is pointing out of the page, so you can use the right hand rule to determine the V cross B should be pointing to the left, V cross B by right hand rule, and this is a negative charge, so there will be a force acting to the right side. So FB is pointing to the right side. That's why this, if a current going from bottom to top, the wire will bend to the right side. And if the current is going from top to bottom, it is the other way around, so the force will be acting to the left side. So the wire will bend to the left side. And actually, this is actually the same as the FB equals QV cross B, but here we have a wire. So it is just like Q. Q is Q is I dt. We have Q equals I dt, I times T. If we assume the current is a fixed current. Originally, we have I equals dq dt. But if it is fixed, we can write it as a Q equals IT, and or delta Q that equals delta I delta T. So in this case, we have Q equals IT times V cross B. So this V times T is actually a length. So we can write it as I L cross B. And of course, L is follows the direction of the current. So we have I point to the top, and B point to out of the page. So we have I cross B to be FB. So L has the same direction as the current. So here L point to the bottom. So here L cross B would be point to the right side if you use a right hand rule. So L cross B. Somehow like L cross B, so point to the right side. This side L cross B, point to the right side. So so this is actually another version of the Lorentz force. So here L is a length vector that has magnitude L and is direct along the wire segment in the direction of the current, conventional current. Conventional current means the direction of I. And now maybe the wire is not straight, so we can just cut the wire into many parts, and then we have a DFB equals I DL cross B. So we can cut the wire into this part is a DL, this part is another DL. So maybe they point to different direction, and then we can just integrate them together. So we have a DFB equals IDL cross B, something like this. Okay, so we have a sample problem here. So here we have a straight line, we have a straight horizontal length of a copper wire has a current I out of the page. And what are the magnitude and direction of the minimum magnetic field B need to suspend the wire? That is to balance the gravitational force on it. The linear density of the wire is this one. So here, as long as we have a FB equals I L cross B, which means that we can write it as a scalar form, which is FB equals ILB. As long as we know all the vectors are perpendicular to each other, so the sine theta, which will be a sine 90 degree, which is 1. And so FB is this value, and this is mg. So this is equal to mg. And now, so we can have a B equals mg over IL. Mg over IL. So, and we can slightly rearrange the term so that we have M over L to be a term, we have G, we have I. Because here we have a mass per unit length, so that we put this term together. So this term will be 46.6 gram per meter, which is 46.6 times 10 to the minus third power kilogram per meter. And then I is 28, and then G is 9.8. So this will be 1.6 times 10 to the minus second power T. So which means that if we have a wire and then we have a B field, then this wire can be floating there. As long as this FB is as large as the gravitational force, the wire will be floating. Of course, if FB is larger, then the wire will going up. Okay. Maybe we stop here today.